Okay, ready to go? How was the homework? Question number 1, I guess. Question actually number 0 is, do people on Zoom can hear me? I don't know, maybe on chat you can quickly confirm. Hey guys, stop talking. Let's quickly start. You like to discuss things. Okay, I cannot read Zoom chat, so someone else can tell me. Okay, so what's up with the homework? Was everything fine? Everyone submitted? Okay. Okay, good. So nothing super hard, right? So we will release another homework hopefully today or tomorrow. It will be more about various instruction and coding and writing assembly, but assembly is still on paper. And then next homework will be assembly in the simulator. So we'll cover the simulator later this week, hopefully. When is what? Will be released today. I hope to release it later today. When will it be due? Like let's say Friday or Monday. We can decide. We can say Monday. Just I mean, there is no rush really. Just see, as long as you can take it. What else? No, I think this is it, right? So I pushed my latest slide deck. So let's get back to this to the class. So look, this is where we were last time. So we covered bits of assembly. So we know all arithmetic operations. We know shift, right? And today I'll cover logical operators like or and stuff like that. And so last time we were talking about how to convert if then else and loops into assembly, right? So we know all of this now. We went through those examples. And today, our main topic is to learn how functions or procedures are invoked, right? So it's one of the most exciting topics because right now you can write code. You can even, I mean, it's Turing complete at this point. You have loops, right? So you can write any program you like, but you still need to, I mean, it's still nice to structure any program as a collection of procedures, right? So because just that's modularity, you say, look, this is a vectorial. And by simply looking at the name and maybe like accompanying documentation, you say, okay, I know that this function will compute a factorial. So you call it and you get back the factorial, right? Of the number which you pass as an argument. So let me quickly finish a couple of those logical operations, right? So, and again, let me quickly, so I've seen those questions online on Piazza and on Discord. So do we understand that shift by 1 in a binary system is a multiplication or a division by 2, depending on where you shift, right? Is that clear, or I have to go over it again? Any questions about shift, right? No. So I haven't covered multiply instruction, but you can guess that there is a multiply instruction, and it will be used today. And you can guess what it does, like similar to additions and everything, right? And then later on, we will cover how precisely multiplication is done on real and floating point numbers, right? And so shift is easy, right? And a couple of others which are useful is AND, right? So AND essentially, what it does, it checks if the bits are both 1s, then the result is also 1. If at least one of the bits is 0, right, the result is 0. If both are 0s, then it's also 0, right? So who can tell me under what condition AND is useful? Like, when do we use it?
Great.
Someone tries to tell me something on Zoom? Okay, yeah, go ahead.
Yeah, like a bit mask, so like you only want to check a certain part of the number.
Right, exactly. So for example, remember instruction representation, right? So for example, for those R-type instructions, and this is an example which I was. Hey guys on Zoom, are you saying something, or shall I just, or you will mute yourself? And then a couple of source and registers, destination register, shift amount, and a function, right? And imagine you're just writing a simulator, which like a software implementation of MIPS, and you say, look, I want to know which, what's the value of this op field, right? And how can you extract the value of this op field from this? Like the whole thing is obviously 32 bits, right? What will you do? Like you want to do something like op equals, and imagine this is instruction variable. Imagine we are in C. This is instruction. So then you can't assign instruction because it's the whole number, right? So you have to add something here. What will you add?
So you have a bit mask for like the last 4 ones, so you have like 1.1 and then followed by all zeros. And then maybe like right shift by.
Right. So what you're saying is that what you want to do, you want to mask it with, I forget this field is 5 ones and everything else is zeros, right? Sorry. And that will exactly give you the number which contains only these 12 bits of operation, right? And then you do a right shift. So this is a little bit unnecessary, because if you do the right shift, it will extend the op with the leftmost with the higher zeros, right? So if you really want to do the, if you really want to extract just the op field, you just can do the right shift. However, if you want to extract something like RT, you do the right shift, which gives you everything on the right of the RT, right? So you will have a number, something like 0, 0, 0, and then there will be op, and there will be RS, and then will be RT at the very lowest bit, right? And then you can mask it with a mask which is all ones here, which will give you the value of the RT field, right? No, if I understand, like the question is like, does shift care about the sign? I don't think so. We can double check in the table. Logically, I think no, because those bit mask operations or bit operations, they don't distinguish negative and positive numbers. However, comparisons do, right? And you can load a number and say, you can load instead of loading the 32-bit, you can load a half, for example, 16 bits, or you can load a byte, 8 bits, and then you can, I think, say shift sign extend, because you say this byte is a signed number, and then there will be a machine instruction to sign extend to make sure that 32-bit number actually is signed number as well. But the shift doesn't. So when it shifts, it just puts zeros on the left, right? If you shift to the right. And vice versa, if you shift to the left, it will just put zeros, right? Which brings us to a good question, like how can you multiply a negative number by 2? And I don't know the answer. By shifting, I will verify. So if you come back to me on Piazza, I'll make sure that I understand how it works. I didn't think about it, but that's a great question. Like imagine you have a -2, can you turn it into -4? You probably can, right? Because it's naturally a shift. And if it was signed, but I have to double check if it works this way. You can, obviously, just because if 0 shows up there, and your negative number will be turn into a positive number. But be careful. Like I mean, bit operations are kind of they are very, very sharp. So you have to be very, very careful not to screw yourself. But okay, we got the and, right? And we got the example why we might need and in a field, right? What about or? When do we need or? Or is obviously if either of the inputs has one, like here it's 0 and 1, the result is 1, right? And obviously if both are ones, the result is 1. Both are zeros, the result is 0, right? So what would be a real world example for or? When you're double checking and you I should admit I probably don't get it. But a natural example from a high level language is checking for a flag. So for example, often you have multiple conditions. So for example, A and B, and like A is a student, B lives in Salt Lake, for example, and you can say, you can represent these two flags, for example, as you say that A encoded as 1 in the lowest bit, and B is encoded as 1 in the second bit, right? And then, so this condition, if this bit is set, then A is true. If this is set, then B is true, right? And then you can obviously, to set a bit, you do an OR operation, just adding a bit. And to check, you can again do the mask with a specific bit. So it will be an AND, for example, right? And then again, you can do like a branch instruction on the result, stuff like that, right? Good. Okay, not is negation, right? So here it changes zeros to ones and ones to zeros. And there is also, what's important is that there is a special register 0 on this architecture, which always extends or loads anything into 0, right? So this one to invert the bits, and A nor B. Okay, and someone was talking about signed and unsigned comparisons. So here's the good example. So remember SLT instructions. So who can tell me what it means? Correct. Set less than, right? And so the question here, imagine T1 contains a 32-bit number, this one, right? Which has, what's important here is the 1 in the topmost bit, right? And remember, we know that and like a negative number will contain 1 in the topmost bit, right? And the positive number will contain 0 here. And the question is that if you're comparing with 0, what do you really have to set the, and does this instruction SLT knows whether it's a signed number or unsigned, right? Because everything just comes from memory. So you loaded this register. You, for example, loaded register T1 from memory, right? But at this point, machine doesn't know whether you want it to represent a signed number or unsigned. That's why MIPS essentially, for those instructions and for a couple of other ones, it provides 2 versions. One which operates on a signed version, and one which has unsigned letter here. It says, okay, I will be comparing as an unsigned number. So if you really say that this is an unsigned comparison, then you have to say, you have to use this SLTU instruction, which essentially says, I will compare this to as 2 unsigned numbers. And SLT will compare them as signed numbers, right? So there is this ambiguity. And so they said, okay, we're going to resolve it explicitly because there's really no other way to do that. Is that clear? Sign and unsigned. And we will, as I like, sometimes you say, look, sometimes you need to essentially extend the register. So as I was saying, you're loading a byte, and we'll see that today that it's useful sometimes, and you load the bytes when you represent strings, because strings are individual letters are represented as bytes. And so sometimes you have to, if you have, for example, a byte which is 0, 1, if it's you can either extend it to a signed number or to an unsigned number. So like, which allows you to keep it as a negative number, right? So, and the conversion is simple. So you take the most significant bit and use it to fill up the additional bit. So essentially, if you have 2 and you want to extend it as a as an unsigned number, you just fill the top bits with zeros. And if you have a -2 and you do an unsigned extension, you just fill everything with ones. Great. Okay, so here I'm done with this. So we got the point. So we have signed and unsigned numbers. We have instructions to operate on individual bits. We have arithmetic operations. We have branches, conditional, and we have non-conditional branches, right? And now, like, the core of today is to essentially learn how to call procedures for functions, right? And that's kind of fun because it's a little unusual unless you thought about how to do that. But let me stop here for a sec. So without functions, so we covered a fair amount of MIPS assembly, right? So we probably know how to convert like simple functions. Essentially, most of what you probably write in your in a regular homework. I mean, I don't know what kind of complexity you get in the programming classes. I mean, I'm pretty sure that it gets hard. But something simple like compute simple numbers. I know, like, I don't know, maybe solve quadratic equations, stuff like that. So we didn't have division yet. Okay, we didn't have multiplication, but you can kind of guess that they're around. So there will be a diff and there will be a mul. So you can encode it, right? So any questions about anything what was before that, before procedures? Good. Sign or unsigned? How do you specify it? In a high-level language, typically, remember, I will use C as an example. You write something like int a, and this means that this is a signed integer. So if I say something like int a equals 10, right? It will be sign extend with all the ones, right? Da, 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 da. I mean, I don't know what the binary representation of 10, right? But you can guess it, right? So it will be a signed number. This is how it will be. Essentially, remember, we have a couple of, we have immediate constants. Remember, we can do a load. We can do a load from memory, or we can use an immediate operand in the instruction and encode a constant, small constant there. So you can play with like these two encodings to get essentially, depending if it's a variable or if it's a const, then compiler might generate just immediate values, right? So typically for variable, there will be a location in memory, and this location actually will contain those like 1, 1, 1, and so on until we get to 10. And if you write something like either unsigned in, right, or alternatively unsigned, that's my unsigned, int a equals 10, then this 10 will be represented as, of course, 0, 0, 0, yeah, and then whatever the representation of 10, right? So it will be represented, and that might not be correct, so I don't know really which number I'm representing here, but you got the point. So this is how it is in a high-level language. And in Java, it's similar, right? So Java allows you to specifically, explicitly say whether it's a signed or unsigned. And you have to be careful because, as we know, the range of these two representations is different, right? So here, this number can go up to 4 billions, right? But no, like it's 2 to the power 32 minus 1. But in a signed representation, it roughly goes from minus 2 billions to 0 and to roughly to 2 billions, right? So it's two different ranges. So if you suddenly compute someone's salary and the salary is high, better use, let's say, profit, not salary. Then better use unsigned numbers to make sure that you don't run out of range, right? Because suddenly, if you overflow and you don't detect it, then you can get to a negative profit, for example, right? Okay. So any questions? Any other questions about? We'll take a look a way more detailed look at numbers in the next chapter of the book in the next couple of weeks. Okay, so functions. Functions are fun, right? Because we all know them and we kind of take them for granted, right? And what do you think what kind of assembly is required to essentially have a function foo and call it, right? We kind of already know labels. So you can think of functions as just labels inside. Function name is just location in your binary, right? Which your assembler generates or compiler into assembler. But what would you do here? So you can say, well, for real, we can do some kind of a jump instruction, right? And I don't want to specify, let's assume an unconditional jump, right? So something like J to a label foo, right? Will this work in assembly? No or yes? Why not? Okay, so why do we need to remember where to return? You're right, but tell me the reason. Like, why? Like, imagine there is this label A, which is next instruction after foo. So maybe you can, towards the end of foo, you can jump to A.
We don't have that language. We can't turn back. We can't continue with our instruction sets. Like 1, 2, 3, and on 2 we jump to 20. We're just going to continue from 20 if we don't jump back.
No, but you probably can insert a jump back. Why not? So what is an additional twist here? Right, exactly. So what your classmate is saying is that functions can be called from multiple locations. So for example, this is example of the code. And imagine even this is label A, which is right after this invocation, and this is label B. But inside foo, you don't really know where you were called from, right? Just because it can be, I can say an infinite number. It's obviously over this duration, but many places from which the function might be called, right? And if you're using a function pointer, then you really can turn it into something what is close to infinite, right? So that's why we need something else. So what is this else? Like where can we keep this information about the return address? Say again? Yeah, we can, for example, designate a register. And this is exactly what MIPS architecture is doing. Let me erase everything here. So they say, okay, there will be a special register, which is called RA, return address, right? And they say, well, instead of like saving this label A manually every time you're about to jump, we'll come up with a new instruction, which will do it for you automatically. So they came up with this instruction, which is called jump and link. So essentially, jump and link instruction, you pass a label as an argument, right, to this instruction, and essentially it jumps to this label, but it also saves the return address into the RA or return address register, right? And obviously, how does it compute this return address? Who can tell me? That's a great guess. So current address plus 1, it's almost there. Where do we keep the current address? Remember, there was a special register which is called program counter. You can't really like explicitly use this register in your instruction set, but every time you do a jump, you change this register, right? Right, and so if you have this program counter, then the next instruction is not +1, but +4, because each instruction is 4 bytes, right? So it's literally, it just puts this current value of the program counter +4 into the RA register, right? And this is how you know, this is how you know where to return, right? Logic makes sense? Any questions about it? Let's take a look at the example. No, not example first. There is a little bit more we need to do a couple of things to make sure that we can really write re-entrant programs, right? So obviously we have to make some conventions about how we pass arguments, right? And we kind of talked about it in the past. So you can say, well, I can pass arguments on the stack, or I can pass arguments in the registers, right? Or I can do a mix of both, right? And advantage is that you can say, well, you can pass as many arguments as you want on a stack, right? As long as you have stack space. But every write into the stack memory will take you a little bit of cycles, like 2-3 cycles, right? So it's less efficient than try to pass arguments in registers, right? And so typically, and this is what MIPS does, is that some number of registers and specifically some number of arguments, specifically 4, are passed in registers, and those registers are actually like they are called like A0 through A3. So argument 0 through argument 3 are passed in those registers, right? And similarly, how do we return values? So and oh, sorry, and I forgot. So and if your function takes more than 4 arguments, then the other arguments are passed on the stack. So you essentially, there is a calling convention for which argument goes first on the stack, which goes second, which goes third, right? Right. And so, and these conventions, they vary from compiler to compiler. So you might run into a case when you say, look, I thought that it's done this way. And it's just that you're really looking at a different calling convention. So again, another question. So how can you return values? So typically in those languages which we typically use, you typically return just one argument, right? So usually return an integer, or if you want to return an array or data structure, you typically pass an argument, pass a pointer to this data structure, which is allocated on the heap, right? So, and in some rare cases, you can return 2 arguments, and on MIPS you use again registers which are called V. So for the value V1 and V0 and V1 are the 2 registers which allow which you can use for returning something from your functions, right? And finally, like a little bit trickier case, but as you can imagine, when you call a function, you say, when the function returns, what is the state of my registers, right? So maybe I had some variables into those registers, S0, S1, and so on, right? And temporary registers, T0, T1. The question, what happens to them, right? And what would be your guess? What is the meaningful discipline in order to make sure that we can compose programs like call functions recursively? What can we do with those? We can put them on the stack. So what you're saying is that we can save them and then possibly restore them later. And one way to do that is say, let's save everything, right? All the registers on the stack and then restore them. And then we assume that after the function returns, all the registers are the same, right? It's meaningful and it works this way. But what is the disadvantage? Again, it takes time to save something on the stack. Every time you do a save on a stack, you pay a price of two cycles, let's say. And if you have 32 registers, roughly speaking, it's 64 cycles. So spending 64 cycles on a function invocation, it's too much. And so people came up with a slightly different convention. So question or suggestion. So the slightly different convention is some registers have to be saved and restored, and they like by the function, and some don't, right? So for example, specifically the registers, what contain those values, those S0 through S7, they have to be saved and restored by the function. And registers which contain temporary values, S0, T0, sorry, to T7, they don't have to be restored. They can contain any values. And if the function has something useful in one of those registers, if you have something useful in those registers, or it's called the caller, then the caller has to essentially save the register and restore it after the function invocation explicitly, right? And it allows you to strike the balance between saving everything and saving something, right? And typically you can, like when you look at the code, you see that typically not that many registers need to be saved in the end, right? So okay, so those are actually called. Say again. How are the registers saved, right? So explicitly, the compiler or you, if you're writing assembly, you will generate an instruction which will move this the register into the memory, which is pointed by the stack pointer. And this is, we're going to cover it like in a second. But roughly speaking, it's like it's a store instruction and then a load instruction, which restores the registers, right? As I was saying, it's called calling conventions, and they vary. They vary slightly from architecture to architecture, but you kind of got the main gist. So it's like convention of how to pass arguments, return values, and which registers have to be saved and restored by the function or by the callee, and which have to be, which are not, right? Okay, so just I already talked about it. So passing arguments, first 4 arguments in those registers, A0 through A3. Everything else is on the stack. Return values in registers. So we have two return values, and I mean, compiler can probably use those two. Actually, if you ask me, provide me an example where you really use these 2 registers, and I don't know really. So most of the code which I've seen myself uses just one return value, but I know that it can exist. So maybe a tuple can be returned in this when you have a tuple of 2 numbers, like you're returning something like, I don't know, A and B, for example. If it's a tuple in your language, right, then this can be used. But probably in practice, it's slightly different. And I should probably double check how it works. And again, as I was saying, the convention for registers is that temporary registers don't have to be preserved by the callee. Do you know who is callee and who is caller? So inside the function is, obviously callee, and whoever calls the function is a caller, right? So in the body of the function, you can freely overwrite T0 through T9. There's no convention on preserving them. However, if you try to save something inside S0, you have to first save the original value on the stack and then restore it. Or maybe you can save it in a different register, for example. But typically it's not the case, because you would rather pick a different register to begin with than this one, right? Okay, so let's take a look at a very simple example of a function, and it's called the leaf procedure, right? Leaf means that this function itself doesn't call any other functions, right? So it just computes something and then returns. So we have arguments, G, H, I, J. They are, as we agreed, there are only 4 arguments. So they are in these 4 registers, A0 through A3. The return value F in the B0, right? And let's imagine, for simplicity of this example, that this variable F is actually allocated inside S0. It doesn't have to be strictly this way, but let's just, for the sake of it, imagine it. So let's take a look at the assembly code. So again, leaf example, it's a label in your assembly, right? The machine, I mean, it's a convention. As you say, the stack pointer, you can technically speaking use a different pointer, I believe, even on this MIPS architecture, because you're not restricted. You can choose something else. But the convention is that there is one register, which is called stack pointer. And this is the register which contains the address of memory where the stack is right now, right? So roughly speaking, and we'll get back to it in a second, but imagine you have some memory layout, and maybe there is like text of your program, like binary data section somewhere here, and you say my current stack is just here in memory, and historically stack grows towards 0 addresses. Again, there is no technical reason for that, but it's a historical convention how it's done, right? So this is your stack here. And SP, stack pointer, is a register which contains this address. Your program counter obviously points somewhere inside the text section, because typically you want to execute instructions. There is this notion of a self-generating code, which you can sometimes put instructions on the heap or elsewhere in a data section and execute there. So machine will happily do that, but typically it's not done in most cases, right? So typically your program counter will be somewhere in the text area, right? And we'll talk a little bit about how libraries are linked together. So again, hopefully next on Wednesday actually, but so your PC is here, right? Okay, so what you're doing here, someone was asking, how do you save registers on a stack? So what you're doing here is you reserve space on a stack, right? Because you say, look, I know that I'm the compiler or the assembler. If you write it by hand, you know that I will need to save this value of S0 because I will be overwriting it later in my program, for example, here. So hence I will reserve 4 bytes on the stack. And as I said, the stack grows towards the lower addresses. That's why to reserve space, you subtract 4 from the current stack pointer, right? And you return it, you put the new value of the stack in the stack pointer register. Go ahead.
How do you know you're not overwriting something that's
Right, great question. That's kind of like a philosophical question of today. So the question was, how do you know that you're not overwriting something like a data or a text section? Does anyone know the answer?
You just add, you just subtract it from the stack, so you're adding addresses.
In a normal case, yeah. If you're clever enough, you say, look, maybe I will allocate 4,096 bytes for the stack, and maybe you will be able to do this subtraction maybe for like 1,000 times, right? But maybe you're invoking the factorial function recursively and you invoke it 1,001 time. Then what? Then what? Stack overflow, right? So really the answer on this machine, you don't know. You're just praying that you don't. I mean, there are different techniques to ensure correctness of those programs, right? So you say, wow, we can reason about the stack size, and we can kind of say allocate enough. Sometimes it's impossible because you don't know what the input is. Maybe you're computing factorial of 5 or maybe of 1,000 million something, right? And then you don't know upfront. So there are tricks, like typically there is a trick which allows you to use virtual memory to, let me just show you. They kind of like to, I wanted to actually change the color, the blue. So you can mark this tiny region right below the stack as, for example, read only, or even you can mark it as unmapped, or like, I know that you don't know these words. We'll come back to virtual memory, but essentially the high level meaning is that when you do a read or write into this area, the hardware generates an exception, right? However, you say, look, but what if we'll talk about local variables, or like just a simple example, what if it's not 4, but 4,096? And you, for example, jump over this tiny blue page, right? And no matter how big you make this blue page, you still has a chance of like jumping over, right? So it gets into a hard problem, right? And so the solution is there only in a safe language like Java or Rust, for example. In an unsafe language like C or C++, you're always, it's up to you. So you can always screw your stack, and then that's how the programs get exploited today. But or sometimes you get incorrect results or it crashes, right? Does it answer? Okay, good. That's a very good question. So again, typically it's more we discovered in the operating system class because the operating system kind of decides how to, it's a combination of a language and an operating system to decide how to create this memory layout to make sure that you typically don't run out of stack space. But you're right. Okay, so we reserved 4 bytes here, right? So we save this old value of S0 onto the stack. So it's a stack pointer plus offset 0, right? So with the store instruction, then we're computing the values. So remember, those arguments were inside the A0, A1 registers. We're using the temporal register to compute an intermediate sum. Then A2 and A3, again, T0 to compute an intermediate sum. Then we add T0 plus T1, putting result into S0, right? That's how we decided to write this code. And then since we want to return it inside the V0, right? And there is no instruction in this instruction set which moves the value from one register to another, which is a little bit funny because you would imagine that you can have this instruction, but it doesn't exist. So what you do is you say S0 plus 0, which essentially puts S0 into V0 register, right? And that's where we want to have the return value. What we're doing here, we are restoring the old value of S0 by taking it from the stack where we put it, right, in memory. Since we allocated 4 bytes on the stack here, we are deallocating them because the convention is that after you return from a function, the stack isn't changed. That's yet another convention here, right? So because otherwise you cannot call the functions recursively, or even like once, because your caller will be confused, right? So you restore the stack pointer, like adding 4, and you jump with unconditional jump, passing the array register as an argument, right? So that's the whole function application. You can ask me, just a sec, you can ask me that why do we really use this as 0? It's a little bit artificial because you could probably use V0 instead of S0 in all this like additions, right? And you would be completely happy, and I agree. So a well-optimized compiler would generate a code which would say, okay, S0 is really not needed here, right? So it's just can be optimized out. But for the illustration purposes, just to make sure that we understand how to, you will, in many cases, you will end up in a case when you have to save a register. And the book and I wanted to make sure that we understand that if you need to save a register, which is overwritten locally in a function, you can push it on a stack. I think you were first. Okay, the question is why do we use this add function here instead of a load store, right? So who can give me an answer?
That's a lot faster.
Correct, because store to memory, just the store itself will take you 2 to 3 cycles, and the load will take 2 to 3 cycles. So 4 to 6 cycles you will lose by saving the value in memory. And this instruction can be executed in 1 cycle. I hope your version was the same, right? So there was second one.
So
no, and in this example, we are not saving T0 and T1, right? The question was, is the function always responsible for saving all the register it uses, right? So remember, I just talked about calling convention. The calling convention tells you that the function only has to save and restore registers S0 through S7. I read the book. On x86, I kind of know. On MIPS, I only read the book. If you ask me, do I have to save argument registers? I would say yes, I'm guessing, but I cannot confirm. But for example, T0, T1, you don't have to save, and you freely like put values into those registers, T1 and T0, and say, okay, I didn't care what was there. It's up to the caller to save and restore them. Another convention is the function has to restore the stack pointer, which again, the book didn't mention explicitly, at least when I was reading, but again, I can tell you from experience that this is the convention as well. That answers your question, but and you were add immediate. Immediate stands that you can put this constant 4. Remember, there was like typically add as a opcode, source register, another source register, destination register, shift amount, and a function, right? And shift amount is typically not used unless it's a shift instruction. And add immediate allows you to have a source register, destination register, and a bigger constant in a function, right? So the constant can be, I think, 16 bytes, right? Any other questions?
At the end, when you jump to the return address, that automatically like where at some point set
Right. So you assume here implicitly, you assume that the function was called with this JA jump and link instruction. So yeah, J and link, save, leave example. If you had a program counter here then it will save program counter +4 into the array register, and that's the convention how the functions are invoked, right? So when you say jump through a return, jump returns through a return register, so you just go to the value which is contained in that register. Great question. How do you keep? So that's my next slide. So how do we keep? And you can probably guess how, but okay, I'll tell you in a second. Any other questions about this code? Yeah. What does what? S0. S0. Remember, we talked about it last week. So MIPS has total of 32 registers, and they kind of gave them canonical semantic meanings, right? And S is for kind of local variables which you can use in your functions. Like for example, when you load a variable from memory, you load it into a register, into a set of registers which start with S. I would say it's a stretch, and you can freely load into temporary registers as well. And I would say that like if you look at a real compiler, I'm pretty sure compilers do whatever they want, right? So, however, just the only semantic meaning which these S registers have is that they have to be preserved across the function call. Meaning that if you touch an S register inside your function, you have to save and restore the value which was originally there. So it's more, the semantic meaning is more about the calling convention. And it's kind of convenient, but because on x86, like they roughly just split registers in some random thing. Like ABX and ACX have to be saved and restored, but the others don't, right? And I don't even remember which ones. But here it's easy to remember. S have to be saved and restored, and T temporary registers don't have to be saved and restored across the function boundary by the calling, right? Good. Okay. Anything else? Right. Yeah. So it's just a convention. What's the what? V for the return values. Stands for value, I guess. Value 0, value 1. And A stands for argument. Argument 0, argument 1, 2, and 3. So total of 4. Any other questions? Yeah.
Sorry, what was S?
We don't know. It's like whatever the caller put there, maybe it's nothing, but you still have to obey the calling convention, right? So the question was, what was saved in S0? Unless you have the entire program from the beginning, you don't really know what's inside S0. And there is no convention on that. Anything can be there.
That's why you said the smart compiler, if there's nothing stored, just not save it, right? And skip that step.
No. A smart compiler still has to follow the calling convention. And if it wants to use S0, it has to save and restore it. But
I guess what I should say is the smart compiler wouldn't use that.
Exactly. So a smart compiler would just load or compute the sum inside T0 immediately. And it will, or like even inside V0, I would say. There is a value, right? You don't even know what's there. Maybe 0, maybe any number, right? So if you want to make it, compilers will just initialize it. If you say that it's a constant, they would use like add immediate to put this constant into a register. It's a convention. It allows you to strike the balance. Remember, if you have to save and restore everything, then it's 32 registers, and each save takes 2 cycles, each restore takes 2 cycles. So it's like, what is 64, 128. I said 64 cycles, but really save and restore would be 128 cycles, right? So, and here you say, and it's a smart convention. This is a good example. So people were asking, why is that we're saving only S0 but not T1? Like I said, it's a convention which allows you to strike a balance between what gets saved and on a function application. So here, we really just save and restore one register. That's a huge win over saving and restoring all registers, right? And in typical case, that's kind of representative. You will, in Morse code, which you write, you will only have to save a couple of registers. Yeah. It depends on the store and the load. So for load, its destination is, I mean, the register is always the operand, and the second argument is the address. That's how it goes, right? So for store, this is the operand, and for load, this one is the operand, which you either loading from memory into this register, or if it's a load, right? And if it's a store, you're using the value which is inside this register and putting into the memory, which is in both cases is a second operand. It's an address, right? Good. So everyone is clear? Okay, that's it. Like a very easy example, but we kind of got it. So now let me just do a slight detour. But as you were saying, okay, I wanna hear about how we're gonna call recursive functions. So here is a function foo, which takes an argument a. It's a c. If a is 0, it returns. If what? Yeah. if not, it decrements a, assuming blindly that a is a positive number, and calls itself, and then returns, right? So, and if I invoke it like this with foo 4, right? Obviously, it will be invoked multiple times recursively, right? So how many? 4 or 5 times, right? Agreed. So now we looked at this leaf function, which used this array register, and clearly that you can't do that because you have to do something with this array register to make sure that you can you can call a function recursively, right? I guess obviously, so we will save it where? On a stack, right? And that will allow us to essentially support recursion. So a little bit of a terminology. So non-leaf functions are the functions that call other functions, right? And for these nested functions, the caller needs to save its return address. So essentially, the value of the return register, right? And of course, it has to save its own arguments if it wants to access them again, and the temporary registers, because they will not be saved by the callee, right? So it kind of logically flows from the calling convention, right? And restore them on the stack, right? If you want. So here's an example. So this factorial function, which I was mentioning, right, takes an argument n. If n is less than 1, then return the current value of f. Current value of f. Maybe current value of what? Of n. Not sure what they mean by f from the book. If not, so here you have to return 1, really. And else return n multiplied by the whatever this function returns from a recursive invocation, right? So as we know, n is in the argument in the register a0, and the return value is in the v0, right? Agree? Okay, so let's take a look at how we compile this code. So again, factorial is a label. So now this function says, okay, I will reserve space for 2 elements on the stack, but kind of the same idea. So stack pointer reserve 8 bytes, each value is 4 bytes, so you will have space for 2. And what they do here at the very beginning of the function, typically it's called the prologue of the function, right? They save the current value of the return address register onto the stack, right? That's the gain. You can probably structure those recursive invocations differently, but it's a meaningful convention to do that, to save it right at the very beginning, right? And here, okay, the calling convention, I wasn't clear on that. It actually tells you that you have to save and restore the argument, right? So this argument register is also saved as element 2 on the stack, right? Now we do a check for 1. So if you say, if a is less than 1, t0 is set to 1. And if t0 is less than if it's not equal, what? If it's not equal, okay, this one gets set when this one gets set when A1 is less than 1, right? Like this. If it's not equal to 0, okay, but just if T0 is 0, so if it's not set, right, we jump to L1. So we go here, and in this branch, we essentially construct a recursive call. If we, however, do set it, right? Oh, sorry, if it's actually, yeah, if it's equals to 0, right? So then it's not set. Then if it's equals to 0, not set, we jump to L1. If it's actually set, right? So because, and it's set when the condition is true, right? When it's less than 0, then we don't jump to L1. What we do here is we putting 1. This is the bug in this code, right? Instead of F, you have to put 1, but the assembly is correct, right? We can write to the book authors, and hopefully they will include us into the thank you section of the book. And like 9th edition still, or 6th, pardon. So you're putting essentially 1 into V0, right? That's your return value from the leaf factorial function. You restore the space on the stack by adding 8, and you simply return, right? And it's okay because you didn't override the array register, right? Because here you saved it on the stack, which was a little unnecessary in this case, but you still have the same value inside the array. So you just simply return to the caller, right? If, however, this one is was set, so we if it wasn't set, right? So we jump to the else part of the branch. And what we're doing here is we're decrementing the argument, which is passed inside A0. And essentially, since nothing we already saved the return address on the stack, we can simply call this factorial function recursively. So this is specifically this invocation, this here, right? So when this function returns, we find ourselves here, right? So we restore the original original value of n, which was passed to us inside the A0 register. So when we save it on the stack right here, so this is where we put this A0, right? So put it inside A0, restore the original return address. So since we have to deallocate space on the stack, and since the formula which we're computing, this is A0 multiplied by V0 returned from the recursive invocation of the function. This is what we're doing here. So we are multiplying A0 by V0, saving result into V0 and return, right? So modulo this kind of a tricky condition, which I cannot decipher immediately, everything else is more or less correct, or like not correct, but looks reasonably straightforward. Any questions about this factorial invocation?
In sending registers to the stack, is there a convention for what you say registers?
No, it's up to the compiler to decide the order of how you save. That's sad. There might be a convention. Do you guys know what backtrace is? Backtrace, when you have an exception, you typically get a set of functions which were recursively invoked from main, right? In order to compute this backtrace, the debugging tool or something that throws an exception has to walk your stack, right? And to walk the stack, typically you rely on the debugging information which the compiler generates, right? And so in this case, I think you don't really have to, I don't think there will be a convention on the order, right? And you say, look, you can always tell, compiler always tells you that at this specific point of execution, the stack pointer is such and such, and you can walk up the stack, like and unwind the frames, right? However, if a human does it, you have to do it by hand. And for that, a convention is useful. And I'm pretty sure that that's why a specific convention is used that the return address is saved right when you enter the function. So then the human can actually decipher the stack and do unwinding manually, right? So sometimes it's useful when you don't have those tools. And there is yet another mechanism, which is also referred in the book, which is called the stack frame, which also helps you to do that. That's just for the humans to unwind the frames, essentially. Okay, any other questions? Yep. Last here, right?
Yeah.
So this one is a recursive invocation of factorial with n-1, right? So n-1 we computed here in the previous line. So since argument contains n, so you just subtract 1 and you again pass it as an argument to the next function, right? So a0 is your argument, right? That's your convention. And of course, you save the old value of a here on the stack, so you can know what your n was originally, right? You called the factorial. Factorial did its job. At some point, returned, right? And you find yourself after return on this line, right? On this load line, load war. And so here we're restoring original n into a0 register and restoring original return address, right? Then we are deallocating space on the stack, and then we're multiplying n, original n, by the factorial, which was returned by factorial of n-1, and it will be inside v0, right? Because that's the convention. And so we're just multiplying n by factorial of the n-1 number and putting it back into v0, right? And then returning again, leaving it inside v0 because that's what the convention is. So specifically, remember I was talking about the smart compiler. So this is kind of, if the first example was for illustration purposes, this example doesn't even use any of the S registers. And this is kind of realistic because you don't really have to save anything from the stack here, any of the S registers, because you have enough temporary registers. And you can also use argument registers and the value registers to your advantage, right? And you can, if you need to return something, just simply compute in that V0 register and return, right? Good. Any other questions about recursion? Correct. So to return a value, you just go to the return address. So jump to the return address with the V0 containing return value. Yeah, anything else?
So when you go through, right, so you're adding, jump back up to back.
Yeah.
Resaving all those values, your return address thing changes, right?
Correct. Correct. Yeah, I don't have an animation, but you can imagine that, you know, the stack will be growing for a while.
Yeah.
Because it will be saving return A0 and return address on the stack. It will be growing towards the bottom addresses. And then at some point when you reach this, label here, you start just jumping and essentially restoring. No other questions? Okay, good. So this is more or less, I know that immediately ready to start. We got the recursion. Let me talk a little bit about local variables. So most of the the hardest part is this one. Like this is to understand how to call return functions recursively specifically. Remember, once I asked you what kind of variables do you guys know in my introduction lecture number 2, and we talked a little bit about them, but who can tell me again? What kind of variables do you guys typically should know in a normal language like C, C++, Python? There will be 3 classes of variables. Who knows them? Those are types. String integers are types. Any variable of any type can be allocated anywhere. Local and global, and that's 2 types. And what's the third one? No, locals are on the stack. So dynamic, they go on a heap, right? Okay, let me explain. Let me be specific. So 3 kinds. So globals are allocated in the data section, right? Remember I said when you compile like a program and it's actually saved on disk, there will be a text section which contains all your instructions, and there will be a data section which will contain global variables like strings, for example, or some const variables which you declare here. Typically, you have this funky better safe space section. It's like it's not safe on disk because if the variable is allocated to 0, you don't really have to save a bunch of zeros on disk, right? To save those zeros, to save the space on disk, people just remember that when you load the program in memory, you just initialize the memory with zeros, right? So because you know that you need like maybe half a kilobyte of zeros, right? And those are the variables which are initialized to 0. So called BSS. But you can forget about this complexity and just think about it as data section, right? Dynamic variables are on the heap. So those come from malloc, or if you're running something like C++ from a new operator. And local variables will be allocated on the stack. Let me just provide some specific examples from the C language. And I know that you learn C++, so it's not too far off. So if you declare a variable in a global scope, right? So global scope, that's where int main is declared. This is a static global variable, so it will go into the data section. If you also use the static keyword, even if you declare the variable inside the function, right, it will be still put in a data section. It's a global variable because of the static keyword. If you erase this static keyword, then it will become a local variable, right? But those two will go into this data section, which I was just describing, right? And those are initialized, so they're not going to go into this BSS section, right? Dynamic variables, which you allocate from those allocation primitives. Typically, it's just a library or part of a language runtime. Kind of, if it's a new operator, it sits behind the new operator, but it will still be a library deep inside, which essentially, if you have the program, if you have the space of your program, kind of like you say, okay, I loaded it, its text, for example, is at address 0, then I loaded my data section with global variables here. Maybe I put my stack here at the very top, it grows this way, stack. Then you say that this space is still unused. An operating system can give you chunks of this space. Like you have a specific system call, which is called SBRK, which says, okay, like, can I get a chunk of this address space? Alternatively, on modern operating system, you use something like mmap, right, memory map. And this unused area essentially then managed by this malloc library, and it creates like metadata, and essentially just later on when you say, I want to allocate 64 bytes, it will take an unallocated part of this area and give it back to you as a pointer, right? And it's like, you can imagine how to manage. You say, you can think of it as a simple bitmap in the most simplest case, saying the chunks of the 64 bits are available, or you can come up with more sophisticated data structures when you can manage this whole chunk as regions of different size. Typically, this is how it's done. Like you can allocate like 32, 64, 128, and other powers of 2, right? So this is malloc or new, and this is called the heap, right? So this area is called the heap of the program, right? And so you use typically malloc, and then you use free to essentially deallocate it, put this like put a previously used chunk back into this pool of free regions, right? And finally, you have local variables. So variables which are declared inside the function, right? So you're in the function scope, which starts here, ends here, right? And so this variable is actually allocated on the stack. So like if you say int a b equals to 33, those a and b will be also allocated on the stack, and they will be deallocated when you exit from this scope with this return statement, right? So is this like, I don't know how much you know about it. Is it like this idea is brand new? You never thought about it before, how these variables get allocated? It depends on which language you used before. In Java, you don't have to think about it because it uses a garbage collector to manage your memory. In C++, if you try to return something like an address of B here, like of this B, and imagine if you're returning a pointer to an integer, you kind of screwed at this point, because the moment you leave the function, this B is undefined because it was allocated in the stack, and now the stack is used by something else, right? So like you have to think a little bit about it. Okay, so what's the purpose of local variables, right? Imagine we have a function foo. It has 3 local variables, a, b, and c. And again, we are invoking foo recursively, right? So each of this foo, every time you invoke foo, like foo, and then you invoked foo again, and then you invoke foo again recursively, you need a space for this a, right? So it has to be different a's, right? So a0, a1, a2, and so on, right? Every time you invoke foo, a has to be different because it's really assigned differently here, right? So that's why this space should be associated with the scope of the function and should be alive for the duration of the scope. But at the same time, the moment you return from a function, you say, well, the space is probably not needed anymore, right? So that's why it's logical to put those local variables on the stack, right? So it's in a very similar manner how we allocate space for saving temporary values like S0. You will just reserve space on the stack. So essentially, inside the function, when you say, like, I enter my function prologue at the very beginning, you say, look, decrement some space on, decrement the stack pointer, reserving some space for the local variables. And here, for example, if again you kind of like foo here invokes bar, so that was the stack when foo was running. Like again, if I understand correctly, the book here, so it says that if you have more than 4 arguments, so argument number 5 will go into this position of the stack, right? So number 5, maybe number 6, right? So you pass them as argument, then you save the return address on the stack, and stack grows this way. Then you use this space for save and restore to registers, and then the space is used for local variables, right? So if the compiler knows how much space you need, you can immediately decrement this pointer if you keep saving additional registers in some if then else branches. Not on every branch you need to save something, then the compiler will dynamically adjust the value of the stack pointer, and then will be saving and restoring something on the stack. But this is specifically kind of the stack layout. You start with this when you call the bar, and when the bar returns, your stack is restored to the previous value. And remember, my integers a and b, they will be sitting over here, right? So when you return, a and b will be still sitting here, and if you return a pointer to b, that will be a pointer. It will be pointing into that memory. I mean, you might be lucky, maybe that b will be there forever, but maybe you again return, maybe you invoke something recursively, and this b is overwritten with like a return address or something on the stack, and then you're unlucky because b suddenly changes value, right? Good. Everyone is tired with it, and it just again, so we're almost there. Just a couple of final remarks. So this is a typical layout of the address space, which I keep drawing. And again, those layouts can be different and more sophisticated on full-featured operating systems like Linux and Windows. But roughly speaking, you can imagine there is a program text, some area for data section for global variables, some area for the heap, right, which is managed by those malloc primitives, and some area for the stack, which grows down here. If you have multiple threads of execution, then you have a stack per thread, right? And then the idea that the heap and the stack grow towards each other is that you don't have to reserve or fix the size of the stack. As long as they don't collide, you're fine, right? So that's kind of a nice idea of dynamically managing memory. But even if you have 2 threads of execution, so for example, this is T1 and this one is T0, this layout kind of doesn't work. So T3 will have its own stack over here, right? And we're going to talk a little bit about threads, but later. And remember, program counter typically points somewhere at the text section, right? Because it's unlikely that you're going to jump onto your stack. It's possible. Machine will do it, right? Unless there is like a memory protection restriction, which will cause an exception, nothing will happen. And then you'll start executing here on a stack. The stack pointer points to obviously to the stack location, and the GP global pointer points to the beginning of the static data, right? We mentioned it before, right? So any questions about the address space layout? Intuitive or kind of, I mean, it will become more and more intuitive, I guess. And I'm actually, today I'm lucky I made it till the end, right? So just to recap, so this is what we learned today. So this is when we call a function, right? We place parameters in registers. And if we have more than 5, we'll put them in a stack, right? We then jump to the procedure with this jump and link instruction. Then we will reserve storage by subtracting something from the stack, right? So essentially stack goes downwards. And if you need some space, you just subtract from a stack pointer. Then we will do whatever we need inside the procedure, right? We place result into the V0 for the caller. And if you have a more complicated result, V1 as well. And then we will return with this jump return through the return register, RE. So, okay, so any questions about it? If there's anywhere, what? Right, the whole work, which will come out today, will be all practice. But a couple of examples which I covered today are in the book as well. Book probably has a little bit more. I think next time I will try to bring the simulator and kind of like we will take a look at real programs, like for real. And we can also use a C compiler to generate something simple, I guess. Okay, thank you so much. See you Wednesday.
So that whole issue with